Talk about a problem in electron molecule scattering today, how an electron hits an H3 plus ion, breaks it up into either 2 or 3 neutral fragments, the process of dissociative recombination. Should preface this by saying that my main collaborator on this work is Slava Kokalin, shown here in this picture, and he's really been instrumental. This work really couldn't have been done without him. He's really done an incredible job on a very, very complicated problem. I think one of the most complicated I've ever tackled. So to begin with, I want to give a few motivations in terms of the overview for this talk, why this is an interesting problem. It's a pretty interesting fundamental problem, and there is an important astrophysical aspect of it, which makes it important to know the answer, not only as a problem in fundamental atomic physics. And there are some sort of conflicting experimental and theoretical evidence on what really is the bottom line, what is the rate coefficient for this reaction to occur at low energies. And so I'll describe that and a paper that we published in Nature about a year ago, which proposed that the mechanism controlling the dissociative recombination is actually a Jahn-Teller kind of coupling. And then finally, some very new work which has implemented a full calculation based on this mechanism that is, I think, coming close to resolving a lot of these controversies and questionable issues. So first of all, let me just remind you what H3 plus looks like. It's a nice little equilateral triangle molecule. And that means it has this D3H symmetry group property. It's a very stable ion. It exists out there in the interstellar medium a lot. And of course, since there's a lot of hydrogen, it's very important in astrophysics. H3 plus was discovered in the Great Orion Nebula in the mid-90s by Oka in absorption spectra. And it's important for a number of reasons. One of my interests is, and the sort of interest that would, I think, Ugo Fano would really relate to, is that it's really the simplest polyatomic molecule. And in that sense, it's really a prototype and can serve as a benchmark for our understanding of how an electron interacts with all the rotation vibration degrees of freedom in a polyatomic molecule. Now, one of the interesting things from the astrophysical point of view is that a lot of the molecular chemistry hinges on how much H3 plus there is out there. And so H3 plus acts as a proton donor in a lot of these chemical reactions. So it's pretty important to understand how easily it is destroyed by low energy electrons in that environment. So this is kind of the reaction chain, how H3 plus is formed. Just to point out, it's usually made by a cosmic ray ionization. It makes H2 plus, which then can react very efficiently with neutral H2 to make these H3 plus ions. And these are, for instance, the absorption spectra of Oka and his collaborators that have seen these spectral lines in the infrared, demonstrating the presence as you look on a sightline to various objects in diffuse interstellar gases. Now, there are some, depending on the molecular clouds you're looking at, there are varying densities of these ions. It looks like, for instance, in diffuse interstellar clouds, there is a puzzle that how could you get this number 10 to the minus 7 per cubic centimeter because from the measured destruction rate coefficients for H3 plus, you just wouldn't expect this much to be left over. That's still a bit of a mystery, although there was some work by Alex D'Agarno's group which suggested sort of a clump model that might be consistent with the terrestrial measurements of dissociative recombination. But there is still a bit of a mystery there, and that's a little bit unresolved. But the bottom line is that it's pretty important to understand what really is how fast this reaction occurs when an electron smacks into this H3 plus ion and blows it apart. Now, this is the story of Earth-based measurements. Mats Larsson's group has, in the Cry-ring storage ring, and there have been other storage ring measurements that are also seeing this 300 Kelvin rate coefficient of around 10 to the minus 7 cubic centimeters per second. But there's a bit of a puzzle because afterglow measurements are seeing 1 or 2 orders of magnitude smaller rates. And so it's a bit of a mystery, really, what is the rate? And that's one reason why it's kind of important for theory to understand this. This is the Cry-ring experiment. And this is all the stuff they use, and the food items they consume in order to try to make these measurements to figure out this rate.
Convincing.
Okay, so now, in terms of trying to tackle this, there was some theoretical work before we dived into this. But as you might imagine, when you have so many degrees of freedom, you've got all the different ways an H3 plus ion can rotate and vibrate. And then you add an electron and its three-dimensional motion to that. It's a pretty complicated many-body system. The type that the techniques developed by Ugo Fano are very helpful and really instrumental in trying to get to the bottom of this basic question. But the theory in reduced dimensionality models, where you just say, well, you're going to, for instance, move one of the nuclei along the perpendicular bisector of the other two atoms, those methods have underestimated by 2 to 3 orders of magnitude the dissociative recombination cross-section. And for instance, this work by Schneider, Orell, and Suzor Weiner that was in PRL a couple of years ago, it was pretty important, though, in pointing out that indirect Rydberg channels appear to control the main physics of this reaction. And before that was realized, the discrepancy with experiments was about 4 or 5 orders of magnitude. Now this work brought it down to just 2 or 3 orders of magnitude. And this kind of shows I think the experiment, and without the indirect channels is down here, and this is sort of with the indirect channels up here. And this is a log scale. So there are a bunch of orders of magnitude problems that have to be solved. Now, in terms of how dissociative recombination occurs, there's a very nice picture. It came, I think, out of O'Malley's work, or maybe even going back to Bates before that, 60s and 50s, which says that basically you have a target potential curve for the ion in a diatomic, for instance, Born-Oppenheimer potential curve. And then if you draw the Born-Oppenheimer potential curve of the neutral, it cuts right through. And so you can sort of think if an electron comes in at some incident energy, it can sort of jump onto this neutral curve and then just simply dissociate away. And the problem with H3 plus is that you don't have this simple crossing. Basically, the neutral surface goes way underneath the ionic surface. And so there is no sort of simple crossing that can happen. And that's what made it very mysterious that the observed rate is as high as it is. And that's why the theory, when you only try to do a direct mechanism, it's orders of magnitude off. This is kind of the theory that comes out. I call this the O'Malley formula, which basically describes what I just described, this hopping on in a simple Born-Oppenheimer picture onto that neutral curve and then dissociating. But now what we are tackling is how to put together the realistic three-dimensional motion of the nuclei in conjunction with the electron motion. And the reason that's important is that we had some evidence that Jahn-Teller coupling is important, and you simply can't describe that with a reduced dimensionality model. So anyway, this is our Nature paper, which talks about this H3+, and there's a nice News and Views article by Anik and Schneider about it, if you're interested. pointing out this mechanism. And I'll show you today, I'll describe the mechanism that goes through Jahn-Teller coupling for this reaction, and then our new calculations that combine hyperspherical methods and multi-channel quantum defect theory and Hugo's vital concept of a frame transformation, puts all that together to really describe this non-perturbative effect. Okay, so let me say some words now about the Jahn-Teller symmetry distortion effect. Okay, now if you look at, basically it's the p-pi states that are controlling the physics that interact strongly. The electron ion interaction is controlled by the p-pi Rydberg state. And in particular, if you look at those, they dissociate either into 3 neutral hydrogen atoms or into H2 plus a hydrogen atom. And these are basically 2 sheets of 2 potential surfaces that have a conical intersection at the symmetry point. And in fact, if you look at the Born-Oppenheimer surfaces and their couplings, they have a divergent coupling right at the D3H symmetry point. As you distort away, you break the symmetry and you break a degeneracy of the p-pi states, the in-plane p-pi orbitals. And what that means is there's a huge non-Born-Oppenheimer coupling at that point. So some work that Jeff Stevens did with me in the early 90s looked at photoionization of some metastable Rydberg states of H3 that had been measured by Hans-Peter Helm's group. And Jeff did a really nice job of sorting out the main symmetry effects and putting in the Jahn-Teller physics. And really all of this new work on the dissociative recombination of H3 plus is kind of triggered by the observation in those calculations that the broadest autoionization features in the spectrum are like this one, aside from rotational autoionization, which is a comparatively simple effect. But other than that, the broadest features in the spectrum were their decay was controlled by a Jahn-Teller coupling. And so let me try to explain how we put this together with describe it in a vibrational frame transformation picture. Okay, so first of all, a really important paper that really influenced me over the years was Fano's 1970 paper introducing the idea of the frame transformation. And this was sparked by a visit of Hertzberg to Chicago to try to explain some spectra of H2. And the basic idea of this paper was that when an electron, I learned this from Dan Dill and Christian Jung, and have really implemented in beautiful detail this picture in the most complete possible way for the H2 photoabsorption spectra. And really, it's the only way to understand H2, basically today, the rich rho vibrational Rydberg channel interactions. The basic concept is that when an electron is far away from an H2 plus ion, okay, it sort of looks and it sees the ion vibrating and it sees it rotating in a particular rotational state. As it comes in, though, and it's accelerated by the Coulomb potential energy, it's moving so fast that it just zips in and zips out while the nuclei are basically frozen. The short-range part of the collision happens so fast compared to nuclear timescales that at that instant, that very short-range interaction is really, really well described in a Born-Oppenheimer approximation. However, when it gets far enough away, it's no longer Born-Oppenheimer. The Rydberg electron is pulling away very slowly, maybe from one ionic threshold. And so really the nuclei are moving now on the timescale of the electronic motion. And the beautiful idea of Fano is that simply by projecting those long-range states onto the short-range states, you could describe how the wave function of the electron evolves as it goes from the short Born-Oppenheimer region into the long-range frame. That's the whole concept of the frame transformation. And now that's been extended. Fano's original paper was just on the rotational aspect, and then Dill and Jung extended all this to include vibrational and even dissociative physics and diatomics. And a pretty a paper of Fano and Liu that had a lot of foresight started talking about extending this to molecules like H3, and understood that you have a similar thing, that when the electron is close in, seeing this equilateral triangle, the wave function has these D3H quantum numbers. And now the frame transformation has to involve this projection of the D3H quantum numbers onto everything. Okay, so do I want to do this? Yeah, I think I do. Let me just show you kind of a quick cartoon that shows what this Jahn-Teller physics looks like. Basically, what we are saying is happening when the electron collides with the ion is it excites this type of nuclear motion that essentially sort of each, that's a dissociative collision of an electron with the ion. And it sort of makes each nucleus go in a kind of a vibrational angular momentum, each tracking out its own little circle. That's the motion that is coupled in really efficiently by a p-pi in-plane electron orbital. Okay, so let's come back to this. Okay, so now for the next part of the problem. We have this very nice picture for diatomics, how dissociative recombination occurs. You have one adiabatic coordinate, which is the inner nuclear distance, and then you have the electron motion coupling into that. And it's mostly the radial degree of freedom. Now, just kind of backing up for a minute, we've already heard today how hyperspherical coordinates were a useful thing that Fano really pushed to try to find one collective coordinate that controls the main dynamics of the system. Then he also pushed things like quantum defect theory, where it's kind of a similar concept where you pick out one coordinate in the problem, in this case the electron radial distance from the center of mass of the target, and you postpone solving the Schrodinger equation in that coordinate, or postpone applying boundary conditions in that coordinate. In a sense, I think that's the most general way of looking at all of these methods as kind of an outgrowth of the same concept, is that they're all kind of deliberately postponing the solution of the Schrodinger equation in 1 or 2 degrees of freedom, and then so you can actually get pictures and plot things versus those coordinates and see where couplings occur in space and in energy. That's kind of my most general statement of the multi-channel quantum defect viewpoint that Fano pushed so far, and which is now being extended in so many directions. So now what we're going to do is apply that same idea. We're going to pick out a coordinate for the triatomic ion, and that's going to be the hyperradius. We're going to single it out for special treatment by solving the Schrodinger equation with that coordinate held fixed. And so to do that, we have a hyperradius we've already heard about, and some hyperangles. We're going to solve the Schrodinger equation in all the hyperangular degrees of freedom and get potential curves. And let me maybe skip the details about that and just show you the kind of potential curves. Basically, what we're doing is solving a Schrodinger equation in a hyperangular space that looks like this, a two-dimensional partial differential equation at each hyperradius, which is finding how the waves sit at all the different orientations and shapes of the triangle. And whereas the hyperradius is sort of like the overall size of the triangle.
So is there an electronic structure calculation going on here?
This is all based on the ground state surface for H3 plus that we take from quantum chemistry, which is known very accurately for H3 plus. Okay, so these are then what the hyperspherical curves look like, labeled by D3H quantum numbers. Okay, so it's energy versus hyperradius. And then once you've done this, you can see when you have potential curves that are this nice and parallel and don't have crossings, an adiabatic approximation can be very effective. And so now you can find the energy levels of just the ion. We haven't brought in the Rydberg electron or the incident electron yet. But just focusing on the ion, you can just solve these one-dimensional equations and get the vibrational spectrum. These are sort of how the different adiabatic vibrational eigenfunctions look like. And you see the D3H symmetry kind of jumping out at you. Very symmetrical, of course. And this table shows sort of how well is the adiabatic hyperspherical approximation doing, just for the ion. And you see we have sort of 10 wave number, 10 to 50 wave number accuracy for the lower vibrational levels of H3+, which is good enough compared to the vibrational spacing of maybe 2,000 or 3,000 wave numbers that we think that this is the adequate description of the vibrational dynamics if we just remain at the adiabatic hyperspherical level. We could include coupling terms if we wanted to do better, but really for how far the theory is now and how big our problems are, these orders of magnitude problems, we think this is the least of our problem, really. Okay, so now here's the picture of trying to put in what the Rydberg electron does, or the incident electron. Here's the ground state of H3+, this dark solid curve, and the adiabatic ground vibrational state of H3+. Okay, so when you have an interstellar median of these ions, the system is sitting in this state here. And now when you bring in the Rydberg electron and just include, for instance, the 2p pi states of the molecule, they produce these states. These are the hyperspherical potential curves of the neutral. And now you kind of start to see how this concept is useful of postponing the solution in the hyperradius. Because now I have adiabatic curves of the neutral that cut right through the ground state of the H3+ ion. And there are two families. This family sloping way down here is going to dissociate into H2 in a vibrational level plus a hydrogen atom. This other family up here dissociates into H plus H plus H, the three-body fragmentation. And so now it starts to look exactly like what you had in diatomics when you had a direct mechanism. We have a curve crossing right through the vibrational ground state of the ion when you go to this hyperspherical picture. Now it's no longer quite as mysterious why you could get a fairly high rate.
Chris, what's varying? You have a family of curves. What's varying from one curve to the next? Just
well,
the eigenvalue, or
yeah, you have an infinite number of eigenvalues at any hyperradius when you solve the full Schrodinger equation, and so they have different numbers of nodes in the hyperangular space for the vibrational hyperangular motion. So that's what's different. These states up here, in fact, I'm only showing every 10th curve. So you have to get up to around 200 excited states before you get to the ones that cut through the ground state. Okay, so there's a lot of hyperangular kind of bending and that sort of motion.
So essentially, you've got a swath of curves that's much more dense than you're showing.
Yeah, that's
here.
right. Yeah, 10 times denser than it's shown.
And that swath is taken into account in your calculation?
Yeah, absolutely. Each of these is going to be a channel, and each of these is a dissociative channel. Let's see, in the interest of time. This is, for instance, what the conical intersection looks like if you go back to the relevant normal coordinates of H3+, the lower sheet that goes to H2 plus H, and the upper sheet that goes to H plus H plus H. And these are the kind of in-plane p orbitals controlling the dynamics. Let's see, let me just summarize the main points, and then I'll show you some results. That, again, the main points of all of the theory that we've put together and combined all these different elements is we start with an adiabatic hyperspherical description of the ion. Then we put in MQDT for the electron-ion interaction. But now it's at a clamped hyperradius. Instead of a clamped internuclear distance like in H2, we clamp the hyperradius and we say that the electron zips in and zips out while the hyperradius doesn't have time to change. And then we do a vibrational frame transformation, and we include the Jan-Teller coupling Hamiltonian, like Longet-Higgins and so on have put in. And the last element, which is relatively new, is we use, for the vibrational channel functions in the vibrational frame transformation, we use Siegert states. And that allows the flux to just go out and dissociate. This is like what the reaction matrix looks like that includes this off-diagonal coupling, which is the Jahn-Teller physics, which Steib and Domke more or less showed how to do. Okay, let me, instead of maybe going through all the frame transformation formulas, they're pretty much a semi-straightforward generalization of the ideas of, as implemented by Dill and Jungen and Fano for the row vibrational frame transformation. But basically, all these different hyperspherical channels of the ion, if we calculate their matrix elements at a fixed hyperradius, that gives a reaction matrix now that says the electron can come in and scatter you from one ionic hyperspherical channel into another one. Then later, when we actually quantize into levels V plus in the potential curves, then we get finally the full K matrix or S matrix for an electron-ion collision. Okay. And there's all sorts of details, as you might imagine, with angular momentum algebra that I won't really get into.
So that's a collision at a fixed hyperspherical radius?
Well, yeah, that's what we start with, but then we sandwich over hyperradial functions, and finally we get the full S matrix for an electron-ion collision.
Just back up. Just wonder what the R was at the bottom.
Yeah, that's hyperradius. This means this is an integral over hyperradius in this formula. That integral up there was an integral done at a fixed hyperradius. Okay. So finally, this is really the lab frame electron-ion K matrix. Okay, and then we end up doing, basically it comes down to doing maybe a few thousand by few thousand MQDT calculation. And I think we ended up spending around 10,000 hours on the NERSC supercomputers to do that, because we need to maybe do it at 100,000 or 1 million energy mesh points, because the resonances are so dense. Okay, let me kind of get to the main point and show you some results in view of the time. This is a comparison of the newest experiment. This is actually a slightly preliminary experiment, but it's not too far from the older ones, but by Mats Larsson's group at Kryring, where they have made a colder rotational target than they had before. And these are our calculated DR rates for ortho, the I equals 3/2 state of H3 plus nuclear spin state, and I equals 1/2 state. And you can see they're showing some structure not seen yet in the experiment, although there's maybe a hint that this dip, common to both the ortho and para, there's maybe some evidence that might be a real effect in the experiment. And some other things like the shoulder seem to be also consistent with the experiment. And if we average that over the nuclear spin, we've done it for a few different rotational temperatures, but basically they're pretty much showing that it's coming in with this newest treatment right on top of the experiment, oscillating more or less around it. Again, with a few discrepancies here, but some of these go away if you just say the rotational ion temperature is a little higher than the experiment thought. But I'm pretty encouraged that maybe this is kind of an indication that the storage ring experiments are right, and that maybe we have a pretty solid understanding of the main mechanism and how to implement it quantitatively for this DR process. The final bottom line that the astrophysicists care about is the DR rate it's usually quoted at 300 Kelvin. This red line is the one averaged over ortho and para, and it's coming out at something like 7 × 10⁻⁸, whereas the experiment is like 1.1 or something like that, 10⁻⁷. So it's within a factor of 2 now of the experiment once we put all this together. I think I'm pretty much out of time, so I'll just summarize. The bottom line is that this is an interesting thing. You normally think of the Jahn-Teller coupling as a static, a spectroscopic effect, kind of an arcane effect that is studied in spectroscopy. This is interesting to me because it shows it's actually the controlling physics in an electron-molecule scattering collision. Basically, all of the DR is triggered by that Jahn-Teller coupling. The DR rates now are basically in agreement, at least compared to the orders of magnitude discrepancy with experiment that used to exist. And there was some suspicion that there would be a big rotational temperature enhancement that might have been causing the discrepancy. It appears that's not the case based on our calculations. So the bottom line is that, and here's the first Fano profile of the meeting, that we've learned a lot from Ugo's way of doing physics. Thank you.